Selamat pagi, Prof. Asma.
Selamat pagi, Bu Rini.
Selamat pagi, terima kasih loh. Ini sudah berkenan memberi kuliah pagi ini.
Assalamualaikum, Prof.
Salam. Oh, oke, Pak Waru juga. Alhamdulillah.
Ya, ini dipaksa Bu
Ini
Rini untuk
akan
company you.
yang akan mendampingi Prof. Asma ini nanti Pak Waru ya, Prof. Untuk ini moderatornya.
Baik,
Kemudian
baik, baik. Insyaallah,
selain
boleh.
mahasiswa kami, ini ada beberapa juga kolega-kolega dari perguruan tinggi lain di Indonesia,
Oke, baik,
dari
baik.
Indonesian Association of Higher Education and Electrical Engineering.
Baik.
Eh, itu ya, jadi eh, terima kasih untuk rekan-rekan semuanya dari Forte, baik Forte pusat maupun Forte Jawa Timur ya, atas kehadirannya. Ini Prof Asma, kami mohon izin untuk merekam karena
Boleh, boleh,
jadi
boleh.
kalau misalnya yang nggak bisa hadir atau terlambat itu nanti
Ah,
pulang kembali begitu.
boleh,
Ya.
insyaallah, boleh.
Oke, terima kasih. Berhubung ini sudah lewat satu, langsung saya serahkan ke Pak Waru. Monggo Pak Waru.
Nah, baik, terima kasih Bu Rini. Eh, saya akan memandu mulai dari sekarang sampai insya Allah nanti kalau terjadwal 2 jam waktu yang sudah dialokasikan. Jadi hanya saya kurang tahu apakah nanti 2 jam akan terisi penuh oleh lecture dari Prof. Rashid atau ada sedikit waktu untuk discuss, tapi itu nanti saja. Nah, jadi sementara diasumsikan 2 jam ini untuk lecture saja dan kemudian nanti oke kita akan spare waktu mungkin 20-30 menit untuk discuss. Baik,
Insyaallah.
saya mulai terlebih dahulu. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Alhamdulillah.
Selamat pagi, salam sejahtera untuk semuanya. Salam sehat untuk kita semua. Semangat pagi terutama pagi-pagi kita sudah akan mengikuti lecture dari Prof. Rashid yang insya Allah akan sangat menarik dan akan sangat inspiratif untuk kita semua. Sebelum perkuliahan dimulai, saya akan membacakan terlebih dahulu eh, CV singkat dari Prof. Rashid. Ya. Baik, Prof. Rashid dengan nama lengkap Profesor DS ini sepertinya teknologis, Dr. Asma Rashid bin Poniran. Beliau adalah dosen di Fakulti Kejuruteraan Elektrik dan Elektronik Universitas Tun Hussein On Malaysia. Saat ini beliau sedang menjabat sebagai dekan Fakulti Kejuruteraan Elektrik dan Elektronik dan beliau juga menjabat sebagai profesor. Tulisannya VK7, saya tidak tahu persis VK7 ini apa, sepertinya grade untuk profesor yang penuh ya. Nah, beliau menempuh studi di Universiti Teknologi Malaysia untuk mendapatkan sarjana kejuruteraan elektrik kuasanya pada tahun 2005 dan kemudian menempuh doktor falsafah kejuruteraan elektrikal atau elektronik kuasa ya, dalam hal ini elektronik kuasa atau power electronics di Nagaoka University of Technology pada tahun 2016. Nah, eh, keahlian beliau terutama secara umum di electrical dan electronic engineering, wabil khusus expertise beliau adalah di power electronics, di mana research interestnya meliputi power electronics and drives, power converters and control, kemudian industrial batteries capacity restoration, demand side management of electric power consumption, dan juga ada interest pada underground power cable system. Uh, saya kira itu yang mungkin relevan untuk kita ketahui mengenai Profesor Asma Rashid bin Poniran di sini. Baik, untuk tidak terlalu lama, saya persilahkan Prof. Asma Rashid untuk memulai lecture-nya. Layar dan waktu kami serahkan pada Profesor.
Ya, baik,
Silakan,
baik,
Prof.
baik. Terima kasih. Uh, so ada sedikit. First of all, Assalamualaikum dan selamat pagi semua. Salam sejahtera. Terima kasih kepada Ibu Rini, kepada kepada Pak Waru kepada semua yang terlibat untuk mengikuti program lecture, invited lecture, I think, this event. So, saya akan kongsikan beberapa perkara lah yang mungkin relevan untuk dikongsikan. Dan ketika perbincangan ni, I assume this is only discussion between us. So you can interrupt, so we can clarify something that, for example, you're curious about anything, so we can discuss, we can get clarifications on that particular matter that you raise. So I hope this is not one-way communication, this is two ways. So since not only from Brawijaya tahun 3, so I think there are other participants, so we also can discuss, or we can try to raise anything, any issue that maybe we notice this is important, so how we can rectify, or how we can solve, or maybe there are other suggestion from the participant about my talk today. Yeah. So let's begin. So my title, I think it's about, this is, I'm not sure this is correct title or not. So I assume this is the title that I will discuss today, about the topologies and control strategy for high voltage gain power converters. So why I choose or select this topic? Because this topic is, if you refer to the EV and also for the data center, they are moving from 48 volts to 100 volt to high voltage of DC. For example, for 100 volts DC, 800 volt DC for the EV and also for the data center. So from there, we need appropriate converter that can be used to convert that particular high voltage. So in this case, we call it as a HVDC, high voltage direct current. And also for the data center, for example, any telecommunications provider, they want to spread their signal. So last time they use only 48 volts. So when you use 48 volts, means that you have to increase the cable sizing. Minta maaf, nampak slide saya? Boleh nampak?
Prof, nampak.
Nampak ya? Okay.
Ya.
So because of that, for the low voltage at the input side, means that you have to increase the cable sizing, which is this will be bulky, and also the cost will be increased significantly. So therefore, they're moving from low voltage to high voltage, very high voltage sometimes. And even now, there is researcher looking for 1,000 to 100 volts of DC. So why, when you if you have one power, for example, 100 kilowatts, if you compare with the 400 volts at the output side, also 48 volt. So I think the current will be increased drastically. So from there, if you refer to the I equals to P equals to I square R, means that the I squared, I mean the root mean square of I. So if you multiply by the double up the current, means that the amount of power will be, I mean the current will be very high. So therefore the cable sizing also very high because of the factor of root square there, the square there, means that we need to consider that. So therefore, in order to solve that problem, we need to increase the voltage become high. So therefore, I think this is very significant topic that we can discuss today. So before we go further, so I believe that we need to know about actually what the switches. So there are two kind of switches actually. So semiconductor switches and also the mechanical switches. So from there, we need to know the principle of that, because most of the switching inside the processor or inside in the power electronic technology, actually the switch is very important. So in order to understand that, we need to know the detail about this one. So let me discuss about this part first. The purpose of the switch actually to break down or to isolate the switch from one point to the other point. So that's the principle. And usually the switch, if you have two conductor here, for example, and this is connected to the other part system. So in order to isolate the system, you need a switch. So we call it as a, so when you isolate it, means that there is no current flow. At the same time, the system is not powered up. So therefore, the switch is very critical. So in this case, either the switch is mechanical or the electromechanical. So we have to choose this one, right? So the main switch purpose is to isolate. So for the formal type of switch, we call it as mechanical switches and also solid state. So mechanical usually or electromechanical referring to relay. Relay, if you refer to your car, so it's actually inside the car for the electronic system, it has many relay. For example, to control your headlamp, to control your infotainment system in your car, actually they use relay. So relay is referring to the two magnetic components that will on and off the switch. So therefore, the circuit will be isolated, turn on or off. So that's the typical example. They're using 5 volts system. The other time, the second type actually relay is solid state. So this is what we use now in most our system or electronic system. So from this statement, solid state switches more reliable and exhibit a longer lifetime than electromechanical counterpart to the superior resistance, shock, vibration, and mechanical. They offer faster switching time. So the keyword now is faster switching time. However, the solid state switches have higher insistence loss and also the communication. So means that the keyword now is faster switching. So if you use relay, actually how fast you can turn on and off in 1 second, for example, as compared to the solid state switches. So therefore, faster switching time is very important term that we have to focus on this part. That's why most of the system now, they use the solid state switches as compared to the mechanical or mechanical switches. Ideal and practical switches in static mode and dynamic mode behavior. So usually the switch either on or off state, we call it static condition. Dynamic condition transition. So for example, you have this switch. So on completely on and off, we call it as static conditions. Transition during on or transition during off, we call it as a dynamic condition. So this is, we should know about this because if, for example, if you have one chip, inside the chip, it has millions of semiconductor devices there. So you have to focus on this part as well because this is very important. Okay. If you have this kind of circuit, you have I the function of t, for example, then across the switch, the open circuit here, you have VT. And the other part, you have negative part. So if you open the circuit, the current is not flow. So means that if you refer to the graph, so the I must be maximum. The I must be maximum. At this time, the V must be 0. So that's for the ideal conditions. Similarly, if you close, just not if you close. If you close means that the current can flow, then the current maximum. So from there, for that condition, the voltage must be 0. So means that if I, the function of t, greater than 0, so Vt, the function of t, must be, must be 0. Then if you open the switch, so the voltage either positive or the positive must be maximum. So during that time, the function of t, if greater than 0, so means that I, the function of t, equals to 0. So this is the rules that we have to concern about. But this is only for the static condition. So we don't focus on the transitions condition, whereby during switch on and during switch off, we also need to analyze on that. Okay. Okay, this is the ideal static characteristics on state able to carry any values of forward currents, as zero voltage drop, zero on state resistance, zero power dissipation. During off state, able to extend infinite open circuit voltage, has zero leakage current, has infinite off state resistance. Ideal dynamic static, zero turn on time, zero turn on time, infinite DVDT rating, and infinite DIDT rating. This is for the characteristic for the ideal statics characteristic. Then, so this is the static performance of semiconductor. So this is practical switch. Power semiconductor switch depart from extent that from the ideal there is a small but finite voltage drop in the on. Even though for the semiconductor switches, even though on stage actually there is a voltage drop, small voltage drop, even though the switch is closed. You have the kind of skid. Even though this is closed, for the ideal must be zero the voltage, because the arrows, the current will be flowing from terminal A to B, for example. So when the current is flowing, practically, I mean for ideal condition or for the ideal condition, we across this terminal A and B must be zero. But for the semiconductor, it has voltage drop. During off means that this is open circuit. Suppose the I must be zero. The voltage is across it. Okay, but for the semiconductor, it has we call as a leakage current, even though the switch open. Why? Because of parasitic components. Actually, when it has the gap here, it has the parasitic component capacitive parasitic component. So therefore, there are a leakage current because semiconductor switches is very small, very tiny. So it's I mean, many parasitic component will be considered for this condition. In this case, it has the parasitic capacity. Also, actually, it has the also leakage inductance current. Yeah. Then the leakage current that flow, of course, by the power dissipation of the devices. And usually power dissipation is due to leakage current is small comparison to the power dissipation only. Therefore, the power dissipation of leakage can be neglected. Dynamic performance of semiconductor for the practical switch. Limit the highest repetitive switching frequency possible. Introduce additional power dissipation for the switches themselves. So that's the two major consequences for the practical switch or semiconductor switches. So this is the model. Maybe we can refer this kind of model for the semiconductor. For example, you have MOSFET, for example. So the terminal, source terminal, and this is gate terminal, for example. So this is connected to the source, and this is, for example, this is ground. And in order to turn on this semiconductor MOSFET, you need a gate signal. Okay. Therefore, you need to generate the gate signal here. Gate signal, either by using FAG or any electronic or digital devices, or you can generate that. What kind of signal? Then after that, the signal usually from this gate signal, for example, for digital, I think between 3.3 volt until 5 volts. So very small. Whereby for the practical MOSFET, you require 10 to 20 volts in order to to open the latch or to latch the or to turn on the gate, this MOSFET require this kind of voltage. So therefore, you need GDU, gate driver unit. Yeah, from there you need to feed to this, and this is the grounded will be shared here. Okay. In the GDU there are galvanic isolation. Sorry, I think this is not correct. Okay. So in GDU, actually they use the isolation technique, isolation method. So they're not directly connected from, the signal system to the GDU. So therefore, they use either for using optical isolation, or they're using inductive coupling or isolation here. So therefore, this part will be connected here. Then this is become the voltage shift become 10 to 20 volts. Then will be, if 20, for example, 15 volt here, so the MOSFET will be latched, and then after that, the current will flow, IDS here, will be flow from D to S. If the gate signal receive 15 volt positive. Yeah. Okay, I have a question. So anyone can answer this question. How to turn off semiconductor devices? In this case, for example, MOSFET. How to turn off? How to completely turn off? Any try from
May
the audience?
I
Ah,
answer?
yeah, sure, Pak Bro.
Uh, the practical way to turn off the MOSFET is to discharge the gate charge, so the gate will be empty.
Okay, Disha, yeah.
So yeah, discharge
So,
the gate, so the channel between drain and source will be diminished.
okay, that's the concept. So practically, how to turn off, completely turn off?
Yeah, okay. Give the voltage between gate and source to 0 volt.
Okay, is it true? Can you confirm the zero can be turned off? I mean, you can use you can give zero voltage to the gate, but you really give zero voltage in practical aspect.
That's the ideally
Okay,
ideally
ideal. Yeah,
situation.
ideal. I agree, ideal. But for the practical,
Practically, that's the usual practice. Usual practice.
okay,
You give the 0
zero.
volt.
Zero. If you can give zero. If you
Yeah,
are not giving the zero, the MOSFET will be turned on actually.
turn on.
So therefore, the practical from the industry, you must give the negative 15 volt to make sure this is really turn off. That's why if you refer to the any spec of the MOSFET, usually for the VG between 15 volt to, positive volt to 15 volt. Because in practical, we cannot sure we cannot sure that zero can be given to the gate. That's why usually they practice for negative. For example, if you give 10 volt, means that you need to give another negative volt in order to make sure that the MOSFET completely turn off. So that's the practically aspect. Then after you give this 50 volt, so this will be open, means that the VDS will be maximum. So therefore, the GDU here must be able to generate positive and negative volt. This is for the practical and also for the high current system. So this is very crucial. Otherwise, you assume that the MOSFET is off, but actually it's turning on. Something like that. Okay. So this is the signal from this GDU. I assume this is 15 volt. Okay, so it's fine. Or for the theoretical concept, this is high. Okay, high. You give instruction to the MOSFET here with this time, but it has some delay actually. Practically, it has some delay. Even though you give this instruction turn on, actually start turn on here. So there are delay. So we call this one is TD, time delay, this one, or delay time. Then after that, after delay time, then turning the voltage is decreasingly, gradually decrease. Not sharply, not drastically zero, but is gradually. So we call this one is TR. TR stand for rise time. So usually there are many they use many caption here. You can use any appropriate caption. So in this case, TR rise time. So this is the voltage is turning off gradually. It's not sharply turn off, but gradually turn off. It's not turn off. Actually, the voltage gradually decrease, become zero. At the same time, the current will be increasing. So if you refer these conditions, actually it's not sharp. I mean, this is not digital system. This is state analog system. Therefore, the switch, I mean, the response is not suddenly can turn on or off. It requires some time. So this transition we call as a dynamic mode of the switches. So therefore, this is the part that we have to analyze. And this is we call as the switching loss during turn on. Okay. So after that, after the V completely turn on, I mean, or the voltage is completely zero, almost zero. Suppose zero, but actually it has the voltage drop here. It's not completely zero, even though the current is maximum here. So during this condition, the switch is completely connected between two. It has the voltage drop here, small voltage drop. So this time, this condition we call as a conduction time, or TC. This one TC. From here to here. Then after that, the GDU, we give instruction to be turned on here. Must be turned, but it has some delay. So after some time, we call this is settling time, this one. Storage time. Then after that, sometime, then the voltage is rise again to be turned off to get maximum. So the current is decreasing to be turned off. And this is we call as a fall time, or TF. This is during dynamic condition of the switches. This one. And then sometimes we call this one is switching losses during turn off. So therefore, in order this characteristic, we have to understand actually the characteristic of the switching behavior of each device. That's why in market there are many types of semiconductor devices and many specs there. So you have to choose appropriately, because inside that data sheet they provide several parameters. From there you have to you need to refer, and also from there you have to make sure that the system that you want to apply is appropriate what you need. Okay, then after that, if you plot the power loss graph here, so during transition here, the graph something like this, the power during turn on loss. Then after that, This is for the conduction loss, and this is for the turn-off loss. So this is the characteristic of the semiconductor. That's why one of the importance or critical losses in the semiconductor actually the switching loss and also the conduction loss. That's why diode will give very high conduction loss as compared to the MOSFET or IGBT. But IGBT you need a control. MOSFET you don't need a control, isn't it? Something like that. You know, diode is very easy, but it will give you very high conduction loss. Meanwhile, for the MOSFET and IGBT, it has very small conduction loss, but you need to control. That's also the issue that you have to look in. So therefore, in this case, so there are three type of loss. Number one is the turn for the switching loss. There are three types: turn on loss, conduction loss, and also the turn off loss. And then you also can model it, the switch. Let's say this is your gate driver terminal from high potential to the low potential. Then this is your output power. I mean, the output will be give to the loads. So this is input power, and this is the ground. So if you model this one, you can get these equations to represent this condition or this gate. And you can simplify with this. Usually the gate is very small. It's about, I think it's about 300 milliwatt. It range from 300 milliwatt to 400 milliwatt, something like that. Very small. Sometimes we just neglected about that. So from this, there are any additional loss, and we call it as a gate driver power input loss. Usually we just neglected this loss because very small loss. And from this, you also can derive the equations to represent that conditions. So this one, we can integrate area under the graph of the power, then we can get actually how much the watt for that. For the turn on loss, we can use these equations to represent this condition. Then for the turn off, we can use this. Then for the conduction, we can use this. Then finally, we also can get the power dissipated. This power dissipated of the unit is watt. Okay? So otherwise, we can use get the joule unit. And then for the switching, you also can convert switching frequency 1/, switching period. Okay, what important to consider loss about switches to ensure that the system operate reliable under the prescribed ambient condition, so that the heat removal mechanism, for example, heat sink or radiator or coolant, can be clearly specified. Heat sinks and other removal system are costly and bulky actually. So we need to consider this. Why? Because most of the system now, they have to increase the power density. Losses in switches affect the system efficiency. If the power is not cool in the specified junction temperature, the power capability of the switch cannot be realized. The rating of the power switch rating may be necessary. So you have to consider that. That's why even though only the loss hit watt, but it relates to the other things because the switches must be cooling down. So therefore, how to cool it? You need the cooling system. So or heat removal mechanism, for example, heat sink, coolant, or radiator. So usually you need another system for the cooling system, or fan, for example. So there's also this one also usually bulky, and sometimes you cannot achieve high power density because of that component. Okay, this is example macam kuliah pula. The example, you have this kind of waveform, for example. For the switching characteristics, you have this. For the rest time, you have this 1 microsecond. For the fall time, you have 3 microseconds. and you have maximum voltage 250 volts and the current 100 ampere. So how to get the turn on loss or turn off loss? And then how to get the average power dissipation? Assume that the switching frequency is 40 kilohertz. How to do that? Easy, isn't it? Just substitute into the equation, then you got the answer, isn't it? So this is for the joule. Then you have to convert into the watt. So how to convert that? By multiplying the switching frequency. Then you get that. So my question is, how to derive this one? How to derive? To get this equations during on and during off. How? You need a mathematical skills in it, and you need this waveform to derive. Then after that, you can get these equations or this expression to represent loss during turn on and loss during turn off for the switching. Okay, you just substitute the value V max, I max, turn on, then you just got the value. This is wrong, must be joule, millijoule, not watt. Because this is work, this is joule. And then after that, you times the frequency, and you got the watt. Okay, from this thing, this information, you can convert it. So in this case, we assume that the during turn on, VDS equal to 0. During for this condition. Okay, practical specifications, it has the voltage rating. It has the current rating. What meaning for rating? Forward and reverse repetitive peak voltage on state forward. So what the maximum of the voltage rating for that? For example, 300 volt. So this is the rating. So if, for example, you use for 600, for example, for this rating, you use 600 volt. Is it possible? What happened to your devices? If you use, you buy for 300 volt, but you use for 600 volt, what happened to your switching?
It will break.
It will break because it is semiconductor beyond the rating. Similarly, for the current rating, it has, for example, 30 ampere. It has so you cannot exceed this limit. So how to, after this, we will discuss about how to design. Then it has also switching frequency. And this switching frequency is referring to the speed, how fast your switch on and off. This is also critical. So in order for you to achieve high power density, you need this factor. It's very crucial factor. You need very high switching frequency. But the problem is it possible your device can cope for the high frequency? So that's the other issue. Because sometimes your turn on and off, this one, the IDT rating is very small. So therefore, it's similar to the, for example, you want to use 2 megahertz of switching frequency, but your IDT rating and the VDT rating is very low, it's similar. So therefore, it cannot differentiate either on or off because of this. So means that you need to know the capability of your GDU of your system, is it can provide that, and then you also need to know the capability of your switching devices, your selected switching devices. Is it possible? Is it able to cope up to, for example, 2 megahertz of switching frequency? DVDT rating, safe operating area, and also temperature. This is also important. For example, usually I think 35 until 60 degrees Celsius. So what happens is beyond that? If you, for example, 100 degrees Celsius, so what happened to your system? So you have to consider this. That's why once you designs, you need to consider many factors. The ratings, the temperature, and if high, how to cooling it, what kind of cooling system they use. So there are many factors that you have to. Therefore, the selection of the devices semiconductor is very important. Okay, example. So why power electronic is important as compared to the typical system or the existing system or the conventional system? Why? Okay, you have this kind of circuit. You have this lamp. For example, incandescent lamp. You have DC source. Okay. The input is 50 volt. The output load, these lamps, compare the advantage and disadvantage of realizing the converter using a rheostat and a switch. Okay. So you are using rheostat here. This is 50 volt. The output. Okay. Rheostat. This is the connections. You have source and you have load. Suppose the rheostat is adjusted to give the lamp its rated power. Measurement give a circuit 3.3 ampere and voltage drop at the cross lamp is 12 volt. So in this case, they set 12 volt here. The input 50 volt means that the voltage across rheostat is 50 minus 12 volt. $38 volt. 38 volt. So across it here. But if the current through the circuit is 3.3 ampere, so how much the power at the output side? So P output equals to 12 times 3.3 ampere. So you got. At the same time, the power at the rheostat also will be amperes in it. P rheostat 38 volts times 3.33 ampere. Look at the value. If you compare these both, P rheostat is higher as compared to the output, isn't it? So means that the power dissipated rheostat is higher as compared to the output side. So that we call as a loss. Because you are using rheostat or the concept of voltage divider rule from there. So this is very easy, but it produces huge of losses. So this is the detail. 40 volt, 40 watt. The rheostat is about 300 watt. And this is also loss. So from this condition, so the efficiency for this system, the circuit only 12%. So this is unacceptable because of this loss. Then you also possible to use switch. This is switch. You have the same system, 50 volt. You have same load, incandescent lamp, but using switch. So what will be happening? Okay, the principle, when the switch is closed, the current will flow. And power dissipated the load. Means that the current flow to the output. So therefore the output has 12 volt just now. And times the current, then you got the power in it. Means that the lamp will be light up. Then when the switch is open, the system is infinite. They open, so the circuit will be disconnected. The current can be flow. The power cannot be transferred from source to load. So therefore, the output power will be 0 watt. Easy, isn't it? So therefore, during turn on, there is no losses here. All power will deliver to the load. For this during on, the power also appear here, dissipated here in terms of heat is about 300 watt. as compared to the output only require 40 watt. But for this system, for this circuit, when you turn on, so only 40 watt at the output side. There is no loss here, no loss, which is this is better, isn't it? In terms of efficiency, as compared to that. But this is more complicated because the switch must be on and off, as compared to the rheostat, by using rheostat. Okay, but the problem is if you use switches, what kind of switches? How to control it? So let's we read together. Now opposite the switch can open and close very fast, say 50 cycles per second. Okay. Suppose also the switch is closed only a small fraction of cycle. Do you suppose this condition Islam will be? Since the lamp is connected to the source and small fraction of cycle, it should operate at a reduced intensity and the switch should run cool because the switch many times. 1 second, 1 cycle for 1 second. It's important to operate quickly. So in reality, the electronic switch is needed. So because of very fast, we need electronic switches. The fast operation will allow the lamp to dim without the noticeable flicker and the rapid transition from on, off or off on to ensure that the very little power is taken in the switch. So therefore, you need another method technique how to make sure that you can run the switch on and off 50 cycles per second. So in this case, mechanical switch is not possible. You need to use electronic switch. So in this case, you need a semiconductor switches. So this is the condition whereby during the turn on and off, something like this, the output, this is the output side. Sometime on, sometime off. For the non-critical load, and your lamp will be flicking because on and off, isn't it? So this is not practical in terms of the output side. But this is good in terms of efficiency because the loss at the switch very minimal as compared to the by using rheostat. So how to make sure this is practical? So in this case, we also declare in this case the duty cycle. D refer to the turn on. So therefore, the D equals to turn on divided by capital T or T on over T off. So from this, we learn how to convert this situation into this equation. We call it how to formalize this waveform into mathematical equation. So therefore, this is one of the important things that you have to know. And also, you also learn about the switching period and relate to the switching frequency here. I mean, how frequent on and off. DC we call as a 1 full cycle. Completely on and completely off we call as 1 full cycle. So analysis focus on this part only. Then in mathematics, you can get the equation is something like this. So VDC equals to dVs. I mean, the output DC is influenced by this D. So it's similar concept to the black box. Black box, you have this, the input, and you have this, the output. After you analyze, you don't care what inside the box, but the transfer function for this one is D. D is the factor that the relationship between input and output. So in this case, VDC or V output equals to D V in. So we need to find the transfer function actually for most of the cases. So in order to go deeper in this case. And then in order to ensure that the output from this condition so will be flicking. T on, T on, T on. This is T off, T off. This is 1 full cycle. This is the referring to this circuit, to the circuit, the output is something like this, on and off. So if you connected to the lamp will be on and off, will flicking. But with very fast switching, 50 cycle per second is you cannot see, but it's flicking. So how to ensure that the output something like this? From this, maybe something like this. The output. So it means that the minimum here is greater than zero. So all voltage is over there. And then the power also will be something like that. So you need the LC filter circuit here. L is a instantaneous storage element, similar to for the C, isn't it? But L for current and C for voltage. So means that you can get advantage from this L and C to delay, because for example, for the L, in order, if you less the current flowing inductor will be get charged. But in order to get full charge, it requires some time, isn't it? Something like this, charge and discharge. So means that for this condition, you can get advantage. Something like this, because of this component. Similarly, goes for the C. This is for voltage, this is for current. So means that we call it this is component actually the passive component. So you can get advantage of these two components to ensure that you can get smoothing DC output. And after that, you also can get the constant output power. So therefore, the lamp become consistent. It's not flicking. And at the same
Professor,
time, yes,
Professor,
yeah,
may I
yeah.
ask?
Yeah, sure.
I can see here the switch will cut off the current that flowed
Yeah.
in the inductor.
Yeah.
So the current will be cut suddenly.
Yeah, cut suddenly, correct.
So will not there any effect
Okay, if for
of
example this
the
is disconnected, turn off, then
so
the energy at the C still there, isn't it? Will
yeah,
be discharged. It's something like this.
okay,
The
but
circuit,
the current in inductor suddenly cut also.
yeah, I agree with you. Yeah, it's
There
something like
will
this.
be inductive self-inductance voltage
Hmm.
in the inductor.
Okay. During turn off, so the capacitor fully charged. So means that during that time, only this circuit during off will be discharged to the output. This is still complex case, isn't it?
Yeah, that's
Ah,
okay. That's okay.
Okay. But
But
this
the
is inductor will,
current at induct,
yeah,
the
will
current in
be
inductor will
will
be
be
cut suddenly.
yeah, will be cut suddenly. Correct. You are correct. So if that condition happens, so what will be happening to the output side?
Perhaps there nothing happen in the output side, but the inductor will generate the self-inductance voltage.
Just in the voltage, okay, then.
And the
But
switch will fill the voltage from the inductor.
okay, if you something like this, if you sketch the circuit something like this for this is during turn on.
Turn on,
Okay, turn on.
and then
So in this case, the circuit, I mean the current
yeah,
something
the
like the
current
flow.
is yeah,
So V out equals to VC.
yeah.
Then during turn off, circuit something like this. Correct? Something
Okay,
like this.
correct.
Okay.
But the current at the inductor suddenly cut.
Yeah, suddenly cut. Yeah, correct.
Yeah. As we can remember, the voltage of the inductor is equal to L times di per dt.
Okay.
Over dt. So
Ah,
if there are sudden current value change,
hmm.
there will be a voltage voltage induct in the
Yeah,
inductor.
induce, voltage induce, yeah,
Induced
correct.
voltage, yeah.
So energy is still there because it's not during, I mean, for example, during this time, this is get charging. This is also get charging.
Yeah.
When disconnected, this is something like this, isn't it?
Yeah.
Something like this. So what will happen? This is open circuit.
Yeah.
So the storage, I mean, the energy is still there. But the C will be discharging. But once they connect again, so this one will be charged this. I mean, the inductor will charge the capacitor when reconnect.
Yeah. But
Then
when
if
the switch open,
open,
the inductor current suddenly cut from
cut.
a certain value, drop suddenly to zero. So
Okay.
the I per dt will be very, very high. So the voltage induced in inductor will be very high.
Yeah, you're correct. So that's the condition of this. So therefore, if the circuit is simple like this, happen that, so means that the switches that you choose must be can withstand very high
Yeah.
voltage surge, and also similar to the capacitor and also the source. We will experience that. So therefore, we have to design correctly, and we have to choose the appropriate component for that. Yeah, I think this question is also very important for the VLDI over DT. This kan, okay. Then the major issue power electronic, how to meet the requirement of the load and gain, but with the control, how to improve efficiency for reliable operations, and the saving, how to realize power conversions with less volume, less weight, how to reduce the negative movement and blah blah blah, something like that. Okay, this exercise, maybe if you have time, maybe you can try to prove how to get this equation from this, how to get this. So something like this, you need to focus on this part. And from there, you can derive the equation for example, for VT and IT. Then after that, finally, you can got the work done. Then after that, you also can get this equation. So this is the units joule here. So work done for the switching for the turn on process. Similarly, for the turn off, you can use this equation, this waveform to get this equation, turn on it, V and I. So from there, you can times together V and I to get power. Then you find the error in the graph by using this equation. After that, you can get the work done in joule for the turn on process. And you can prove this equation just now. VDC or Vmax, Imax divided by 6 and times T off or on. Okay, example. Boost converter circuit. How to design? You have this kind of circuit. It consists of one source, one inductor, one capacitor, one switch, and one diode. So you have 4 main components, regardless of the load and source. We have 4 components. Inductor and capacitor as a passive component. You can interrupt me. Then you have 2 semiconductor devices here, diode and also fully control switch. Let's say this is you call as a maybe MOSFET, for example. So only 4 component. With these 4 component, you can step up the voltage. So for this circuit, V out is always greater than V in. So how we can design, we can observe the important parameter for this particular circuit. So during case 1, during switch is closed or turning on. So during switch close, this switch close, so this will be connected. And inductor get charging. And capacitor output side also will discharge to the output side. So from this condition, we can get the appropriate equation to represent this condition. Okay. During switch close, whereby you can refer this equation, whereby VL here, Vs equal to VL, isn't it? Or Vs minus VL equals to 0 to represent this condition. For now, we focus on this part. Then at the same time, for the inductor special, because inductor can store and restore or can charge and discharge the energy instantaneously, because that's the specific feature of the inductor. So VL equals to L di over dt. You have this kind of a form. Sorry, my sketching is not good. Sorry. Okay, in order for you to ensure that the voltage is across it appear, you need the variation of I. In this case, referring to the inductor current. For example, from value here, some value here to here. So there are delta T, delta I, isn't it? Delta IL, for example, in this case. From here to here. So there are changes from low to high, low to this value to higher value. So this one will be appear the voltage from this equation, So one, it has changes of the current, inductor current. I mean, changing must the changing, the minute of changing actually is something like this. You have current here, IL, for example, through this inductor. And inductor itself, it has the feature of inductance. Inductance actually the behavior of inductor. Inductor is component, inductance is behavior of the or the feature of the or attribute of the inductor is inductance. So it is inductance because it's the coil is turning, isn't it? So because of that, it has inductance. So attribute of inductor. So inductor is actually the component. When the current, for example, you see DC current through this inductor, the flux will be formed, isn't it? In order the flux to form, it requires some time. Because of that, the voltage will be appear here, VL. So therefore, you need a changing, or we call it as a charging process. If current through flow the inductor. So therefore, the voltage VL will be appear here based on this equation. At the same time, if, for example, after charge is connected with the resistive, for example, so the inductor charge here will be discharged to the resistive. So therefore, the current will be from here maximum to lower. Okay. So during this time, based on this principle, it also will appear the voltage. So in this case, negative part of voltage here. So this is positive VL, this is negative VL. So that's the special of inductor as compared to resistor. Okay, because of this, we have to consider this condition. So therefore, we substitute this equation into here. So therefore, Vs equals to L di dt. Then we manipulate this equation, become dL over dt equal to Vs over L. Okay. Then from that condition, DIL is, we can equating this into D delta IL and delta T1 equals to Vs or V in over L. We can refer this graph. So minimum, IL minimum and IL maximum. So there are changes here. We try to follow these rules. The different, the changes. From this point, from minimum to maximum. And from this graph, you also can declare that the changes from minimum to maximum equals to delta IL. It follows this rule. And then the changing of time, referring to the minimum and maximum, you can refer this delta IT, delta T1. Here. So from this graph is follow, we can derive the equation, appropriate equation for that. So therefore, we source over L. At the same time, we declare this is during turn on, isn't it? The switch is on. The rising current here referring to during turn on switch. So previously we discussed, we agree that D referring to the turn on time. So therefore from this, you can declare that T on equals to T on, D equals to T on over T or T on plus T or for this one. Yeah, from this you can substitute. You can declare that delta T1 here, okay. Delta T1 at the bottom side here, you can equating become dt because it referring to this time only, on time. Then this one you can substitute into this. Then finally you can get the delta IL equals to Vs over L dt to represent this condition. For the DC-DC converter, delta IL is very crucial, it's very important. Okay. Then for the case 2, switch is reopened. Open. So no circuit here, no current flow here. The circuit something like this. The current flowing here. So during this time, if during the close, this is get full charge, now this one will be discharged to the capacitor, because just now during this time, capacitor will be discharged. During this time will be discharged. During close, switch close, discharge. And this is charged. Then during this time, the inductor is discharging to the capacitor. If exceed, the exceeding current will be go to the output side. So from this, you also can derive the equation. So Vs equals to VL plus Vc, whereby Vc equals to V out. So Vs equals to VL plus V out. Or you can manipulate this equation, VL equals to Vs minus V out. Something like this, by using KVL. Then you also need to include this condition. Actually, the process is similar during turn off. You just substitute, you refer this graph during discharging, from maximum to minimum. So we call this one is T off. T off is referring to 1 minus D, isn't it? This is D on, this is 1 minus D times T. Then you can substitute into this equation. And finally, you got delta IL during turn off. Okay. Then after that, you can combine. So the good thing is the delta here, delta IL must be same during on or during off. So therefore, you can equating together. So after you equating together, then you get the transfer function here. Function. You have this kind of converter. You have the input. This is V in. This is V out. Then this transfer function for this one 1 over 1 minus T. If you assume this is your blackboard, means that you refer this equation. So this is important for you. For example, you want to control it. So you need this kind of transfer function. Then you can get, for example, you have your input 50 volt, and the output you want the output become 100 volt, for example. You just substitute by using equations. So V out equals to 1 minus D Vs. So from this you have to manipulate this equation, become 1 minus D V out over Vs, isn't it? Then after that 1 minus D equals to Vs over V out. So D equals to 1 minus V out Vs over V out. So if you substitute, you can get actually how much the D. So the D, you use the D for the control system, or you can get appropriate output voltage by using this D. So that's for any circuit. Really, this is very important for you to design. So this is in order for you to get the relationship between input and output. Then after that, you also can use this output power to get the average inductor current by using this the process of equating regardless of the losses, P in equal to R. So from there you also can get how much the average inductor current that flow into the circuit. Then after that, why? Because you need this current, average current, in order for you to get maximum current. So average plus half of the delta IL, you can get maximum current. At the same time, you also can get the minimum current. Minus, and this is plus, this is minus. Get actually how much the minimum current and maximum. So therefore, average current, you have to know currents and also the delta IL. So from there you can get. So why this is important? Because you want to find how much the minimum inductance that required for the circuit. So therefore, the circuit will operate in CCM, conduction current mode. So referring to you have this, for example, you have this kind of circuit waveform for the IM. So how much this minimum current? This is 0. So therefore, the current is not reaching the 0, must be greater than 0. Otherwise, will be DCM. This discontinuous current mode. So therefore, this why this is very important in order to find how much the inductance. Otherwise, your operation will be DCM mode. So it's more complicated as compared to the CCM mode. Then you also can find the delta V naught. The delta V naught means that you need to find how much the ripple voltage at the output side, the allowable ripple. For example, you set 5%. The output, for example, 100 volt, the ripple delta V naught is 5% of the V out. So yeah, So I think if you refer to the standard, the maximum ripple must be 5% in order to ensure that the output is not interrupted by the ripple of the output voltage. Or you can get. So this is some example that maybe you can do how to estimate. So this is focused on the design. After that, you can simulate by using any software simulator to ensure that what you design is agree what you simulated in the, for example, by using Simulink or Planks or any software you can use that. Okay, so far any question?
Professor,
Yeah, sure.
we can see there are 3 parameters we must compute.
Mm.
There are L, the inductance,
Yeah.
and then C, capacitance,
Yeah.
and then the frequency.
Mm.
Which the dependent parameter, which one is the constraint? Which
think-
parameter we can choose first?
Okay, first, for me,
Yeah.
I will choose this first.
Oh, the
Because
frequency.
in order for you to design L or C, you need this first. You need this switching frequency. Why? Because, for example, you want to achieve high power density. You try to reduce the size of L and C.
Yeah.
For example, if you use electrolytic capacitor, very bulky, isn't it? If you choose 50 hertz length frequency, for 50 hertz, isn't it? For example, so L will be bulky.
Yeah.
So I think it's not good, but I think for me this is very important. For example, 100 kilowatt, 8 kilohertz, or 50 kilohertz. So usually I prefer this frequency range, 50 to 100 kilohertz. So from there, you can design L and C.
So the higher frequency is the better. But what will limit the frequency value?
Okay. What the limit is your GDU, gate driver unit limitations. What kind of GDU that you use? And then after that, your FPGA, for example. Some FPGA, they only allow for 500 kilohertz, for example, or 100 kilohertz. Maybe one. So the processor, I mean the digital signal generator must be able to generate up to what frequency that we want. Then so the GDU, the delay, the delay will be coped by the GDU as well. And also the semiconductor device, the device also must be able to cope because you need to refer the DI, DT, and DVDT, isn't it? So this is referred to this switching frequency. Because sometimes the delay, this is the, for example, the VDS, this is IDS. This is dynamic mode of the switching. Dynamic mode, the T ni, because we assume this is TR, rise time, must be much more greater than this switching frequency, otherwise will be same. That's why for me, switching frequency first, then the rest will be follow.
Okay.
Any other question?
What is the effect of the frequency to the efficiency of the switching system?
Okay. If you use, for example, many switching higher switching frequency, for example, usually we'll follow the higher switching loss. Higher because in 1 second is more time switching loss, isn't it? So we will cost this one. This is the typical. Higher switching frequency means that will be higher switching loss. Higher switching frequency, you also need to know the devices. I mean, the support. Is it support or not? I mean, your devices will be supported or not? For example, your GDU, FPGA, your DVDTs support or not? You need to refer that. So there are many factors. At the same time, you also need to consider for the power density. Also will be much influenced by the switching frequency. Any
Okay,
other question?
so there is must be a trade-off between
Yeah, trade-off,
the
yeah, yeah,
efficiency and the
exactly. Yeah,
frequency value.
yeah. So that's actually there are one method because of Pareto Frank curve. From there, we can choose the optimum between switching frequency and the power density. So you also can use the Pareto Frank curve method in order to find actually the optimum point. Actually, how much the optimum between efficiency and also the loss. Switching frequency and also loss. So it's power density and switching frequency, how much? Actually, you can use that method.
Okay, that's all
Okay.
now.
Okay, thank you.
Thank you, Prof.
How about the other participants? Is there any question? Okay, if not, we will continue about this. So I think just now we discussed about the requirement of the system. For example, on the onboard battery charger, power converter. So typical board onboard battery charger is large and heavy. Most of the space contributed by the inductor, capacitor, heat sinks, and galvanic isolation, usually by using the transformer. So this is very huge and bulky. But requirement nowadays, we talk about the high power density of the battery charger or power converter. Due to this one, you also need the small size and lightweight. And also at the same time, the efficiency must be optimum or high. So how to achieve that? So otherwise, your system will be bulky and it's not appropriate for the EV or transport. I mean, the application that use power converter. I mean, inside that. So in DC microgrid also it require, for example, a data center here. And also for the HVDC data center is something like this. You can refer this one. So it has many conversion actually from grid to the load. So it has, for example, in this case, it has the DC bus. It convert from about 400 volt from maybe 200 volt or 48 volt if connected to the battery. Therefore, so in this case, higher voltage is crucial due to the cable sizing and also the other factors. So for example, in this case, actually what the power density? What the power density? Is it good, high or low? Which one good? High power density or low power density?
Usually high power density is the better.
Okay, high better. Why higher is better? I mean, power density, if you have high power density, it's better as compared to the low power density.
With a higher power density mean for the same volume for the power converter, we can get a higher power.
Okay, good. Yeah. Or you can refer this analogy. Okay. For example, this dimension, this size, 10 kilowatt, but you try to reduce the dimensions and the size become same power, but the in term of size will be smaller, lighter, and compact. But power is same. So this is what we hope we can achieve that. But at the same time, we also need to consider the efficiency. Is it become the efficiency will be drop or not if we try to make it compact the converter or to achieve high power density? How about the efficiency? Is it we can retain, we can sustain from the previous or not? So that's the issue that we have to tackle. Similarly, with the same size as what Waru said just now, same dimension, we can increase the power, double up, for example. Yeah, that's why easy actually. The problem now is the efficiency. We want to improve as well. It's not only the dimensions of the converter or the equipment, but the efficiency must also be increased. At the what required of the system. For example, efficiency must be greater than 85%, for example. So is it possible to achieve if you change the power? Because for example, for this case, the power is 10 kilowatt for one system, then you want to double up. At the same, you want to maintain the dimension of this system. So usually, if you increase your power, the loss also will be increased, isn't it? Will increase. So how to make sure that the efficiency is minimum, achieve the minimum standard or what the stated by the system. So that's the issue that we have to consider. The factor parameter to achieve efficiency: component, passive component, semi-conductor devices, cooling device, and so other factor. Okay, this is the in order for you to design, actually what the main factor that you have to consider. For example, losses, weight, volume, cost, failure rate. So this 5 parameter is very important for you to design. For example, the cost is low or high. So you or high. And the failure rate, if you make it compact, how about failure rate? Is high or low? Losses, weight, and also the value. So you can consider it. So record the power density of the bidirectional energy converter from 5 kilowatt per Denti cube for 70 kilowatt become 143 kilowatt per centimeter cube. And the watt is 200 kilowatt. So it means that the technology now become able to reduce in terms of size, volume, and width. So therefore, in order to achieve power density, why? Because you want to use that converter into the critical sector, for example, in transportation sector, aeronautic sector, for example, you need to compress to make it compact the size of power converter. So therefore, this is very important from this one from 2004 until 2014. So we make it smaller actually. At the same time, maximum power density and maximum efficiency difficult to achieve simultaneously. We want smaller, at the same time we want to higher power, higher efficiency. Sometimes it's not easy to achieve. But we can find the optimum point between these two because both are very critical, important. Okay, this is the trend now. The devices, I mean the semiconductor devices, the design become smaller and smaller in order to achieve higher power density. Okay, this is what I call just now is Pareto front curve. This is efficiency and this is power density. If you want to higher efficiency, you need to sacrifice the power density, something like that. But you can find the optimum point between efficiency and also the power density. Even though it's not maximum, its power density and efficiency, but you can achieve the optimum point. You are not lost everything. You gain something. In this case, high frequency, appropriate switching frequency selection, balancing of the conduction and switching losses. This is very critical. In order to get higher power density, passive component volume reduction and high switching frequency is required. And also considering the switching loss. Okay, power density. What the main component in power density? Volume of inductor. This is passive component. Volume of the capacitor. Volume of heat sink. And volume of the output capacitor. So this is the major component that influence into the power density in order for you to achieve high power density. For the efficiency, diode loss, diode conduction loss. Then if MOSFET, for example, switching loss and MOSFET conduction loss, wire resistance, inductor couple loss. This is the major component that contribute to the efficiency. So these two, you have to tolerate this element for you to be concerned or to be focused how to get the optimum of each component here. Okay, for example, inductor volume. You can use the equation actually to estimate how large or how bulky your inductor, because inductor usually it require the core, isn't it? Sometimes the core is very huge, and sometimes the core is inductor current is saturated. Then you have to increase the core size in order to tackle the saturated condition. So from there, you also can estimate by using this equation. Transformer volume. Some cases, they have to convert from AC to DC, then DC to DC back, isn't it? So you also need to consider the transformer volume by this equation. You also can get. Then heat sink. By considering the junction temperature, you also can get how large the heat sink need to be used based on the all losses. This volume, then also the ceramic capacity. Why we use ceramic as compared to the electrolytic? Because electrolytic usually for the line frequency, 50 Hz, and the size is bulky as compared to ceramic. And ceramic is very rugged with the ripple current as compared to the electrolytic. So there are pros and cons there you have to consider. But the problem of ceramic, the value is very small as compared to electrolytic. For example, ceramic 1 micro, 2 microfarad, but for the electrolytic maybe 800, 200, something like that. So in terms of ruggedness, ceramic is better. So therefore, for the power electronic, because the switching is very high, so ceramic is recommended as compared to the electrolytic type of capacitor. So from this, you also can find the volume for each component that you use. Okay, there are several kind of arrangement or configuration or topologies or approach that you can consider in order for you to design converter. For example, you use the magnetic base configuration, whereby inductor is a main energy transfer agent from input to output sides, and usually it's need bulky of inductor because you depend on the one passive component to transfer the energy from source to the output. Or you also can consider for the capacitor-based configuration. Capacitor as a main energy transfer agent from input to output side. Usually it require capacitor. Very large actually, huge and large the capacitor for you to be used for that particular system. Or you also can consider both. Inside your converter, it has both combination of inductor and also capacitor as a energy transfer agent, transfer from source to the output side or to the load. Okay, my question is it possible if you want to transfer the energy without this passive component? I mean, without L and C. Is it possible? Maybe from the crowd, from the participant, you want to try to answer? Because I think only me and Pak Baru just the rest just keep quiet. Actually, there are three conditions that we cannot solve any problem. Number one, if all keep quiet. Number two, if all crying. Number three, if all laughing. So these three conditions, we cannot solve any problem. Just kidding. So is it possible you want to transfer energy from source to the load without using any passive component? So in this case, referring to L and C. Anyone?
Well, so far, based on my experience, we still have to rely to L, C, and also magnetic components.
Okay,
We cannot free from the magnetic or capacitor-based component.
Okay, thank you, Pak Waru. How about the others? Do you agree? Do you agree with Pak Waru?
Yes, I do agree, sir.
Okay.
Because even though in the MOSFET itself, there's a capacitance and inductance inside that.
Okay. That I mean, there's one for the parasitic component, but I mean, for the energy transfer, regardless of the parasitic component, is it possible for you to transfer energy from only source to the output without using any major passive component, referring to the LNC? Not for the parasitic, I mean the main energy as a energy agent.
The storage.
Sorry.
I see. If we are looking to the characteristic and from the behavior of the circuit, it's impossible to use none of these things to transfer the energy. Like we need the inductance, we need the capacitance in order to achieve the certain value.
Okay, thank you, Nashua. Thank you. How about the other participant? I think Ibu Rini informed me that I think majority of you is year three students, isn't it?
Yes, actually, not only students, NASWA, for example, semester students,
Okay.
at Bandung Institute of Technology.
Okay, sure. Okay, thank you.
And there are other colleagues also, other universities.
Okay, good. So means that I think many hate. So we can think. So again, my question is it possible for you to transfer the energy from source to the load without using any passive component? So referring to the LNC, is it possible? For example, only switch. Is it possible?
Perhaps we can use non-energy storage, perhaps maybe pneumatics or
Okay.
other kind of storage energy
Okay.
like battery
Mm.
or else.
Mhm.
So, but we must convert the energy form first from electric energy to the other form of energy,
Mm.
and otherwise, so maybe it's not practical, I think.
Okay. Okay, the word practically actually possible, but it's not practical. I think just now we discussed about that thing, isn't it? Previously we discussed actually possible, but it's not practical. Yeah, this one. First, the circuit has no LNC, but we able to transfer the energy from source to the load, but it's not practical because very high loss at the start. The second circuit, this circuit, it has no LNC, but with this circuit, we able to transfer energy from source to the load by using switch on and off. Even though it's not consistent output, it's possible. But we need to install the LC because to ensure that the constant we hope that we can achieve constant energy or power at the output side. So therefore, we put another element, passive component, to ensure that we can take advantage of the charging and discharging of each component to ensure that the power output voltage as constant as possible at the output side. Okay. So in this case, that's why this slide informing that we can use, for example, only inductor as a main energy transfer agent or capacitor. But is it practical or not? Appropriate or not? So therefore, in order to ensure that to be practical and also appropriate, usually we consider the hybrid combination of passive components, and also to ensure that the output side, the output power, including current and voltage, is as constant as possible for the DC. That's why we require that passive component as a energy transfer agent. So therefore, if you combine together, if for example you focus on the capacitor, power DC very high as compared to magnetic base, but we can get an optimum by using hybrid base. If you refer power density versus power. So this is an example of circuit. This is magnetic base configuration. You only use main energy transfer to the output. So this is output circuit. And then we also can use hybrid, means that the energy transfer by using L and C here. So the C we call as flying capacitor. Energy charge, then this is discharge, then charge again. So means there are two main energy transfer agent here, inductor and also capacitor. So for this case, it needs large inductor and bulky. For this case, smaller inductor and capacitor, because two energy storage. So they are compensating each other. And at the same time, you also can optimize the main component here. So this one. Okay. Then this is capacitor configuration, only capacitor here as energy transfer here. Very large capacitor. So means that the power cannot be large. Must be small power only low power. So others will be very bulky. It's not practical at all. So therefore, it's not practical. So by using hybrid, it's more practical to both. And also you can control the surge currents, suppress. I mean the surge current occur, you can control by using, you can manipulating these two passive component to ensure that the voltage surge and also current surge can be suppressed accordingly. This is example from this current and you compare this current. This is also from this current to this current. Example. Okay, then from that circuit, from this circuit, we can get multi-level. So how many level that you require as a energy transfer agent by using the capacitor here, the series of capacitor, and you increase this number of capacitor, the volume of different will be decreased, for example. At the same, you also need to consider the switching frequency, this one. So you can generalize this circuit become better as compared to this one, as compared to either MACD base and also the capacitor base. That's why you have to design. Just now we discussed about the how to design the basic boost converter. Now become is we enhance the complexity of the circuit, become like this, and from this we have you need to analyze. For example, this is the delta IL. This is why, as I informed you before, delta I is very important, very critical, because you want to know how large the inductor, how bulky inductor, and then the attribute of inductor, the inductance, how to ensure that the charging and discharging of the inductor is not long. For example, in this case, for the case number 1, delta IL1, larger charging time, isn't it? From here to here. Similarly, discharging also long time. If you compare delta into shorter, the charging time only this time, then discharging. In order to get shorter charging time, you need to increase switching frequency. But how high the switching frequency is that possible to be increased? So therefore, you need to do analysis. You need to design appropriately. So this is one example. For example, delta IL is depend on the output voltage and also N referring to the how many level. Then you can get, from there you also can get the size of inductor. How small you want in order to make sure that the weight and size can be reduced drastically. So this is the principle, how we can reduce the ripple and why to shorter the charging and this discharging time. So by using this principle, you have to know the VL times TL, voltage across inductor time, charging time of the inductor. So from there, if you refer to this, this is referred to the example for the I think this is 3-level time. So then this is duty ratio. So if you refer this condition, it seems that when beta equals to 133, the gain factor 3, or the duty is 0.25, you can get maximum current ripple here. Once you got the maximum current ripple, you can get smaller size and weight of the inductor, referring to the core of the inductor. So therefore, for the front capacitor converter as compared to the conventional boost converter, you only require 25% of the volume access of the inductor, or in this case referring to the conventional boost converter inductor. Okay, with the same output voltage, the switching frequency and inductor current ripple, the ratio expressed by the equation. So in this case, you only require 25% of the volume access of the inductor. And then from there, you also can find the volume of the inductor, how high the volume. So by using this equation, this principle, you can get. So after you find, you calculate, so you can find that the volume required for the if you install flank capacitor, only 35%. If you compare by using volume of conventional boost converter. So what conventional boost converter? So this is flank capacitor because it has capacitor here. Boost converter is, yeah, this is boost converter. This is boost converter, the CBC, conventional boost converter, something like this. Only this circuit. If you compare, you only require for this inductor, only 30% of volume, and also the inductor only 25%. So you can drastically reduce the inductance and also the volume of the inductor itself. And then if you increase, for example, this is 2 level and 3 level, 5 level, and 7 level. If you plot VT times TL versus duty ratio, you can get actually what duty cycle can reach the maximum of the VT times TL. So for the conventional 0.5, for the 3 level 0.25, for the 5 level, how much is 1? So there, and then you can summarize into this: the inductor percent and also the inductance and co-volume. So therefore, by increasing the level from 2 to 7, you can reduce the inductance and volume, of the inductor. So in this case, for 7 level, they reduce up to 90 to 93% for the core and also 97% for the inductance. So you can go very small as compared to this conventional. So therefore, this is very important for you, to design appropriately of the passive component. For in this case, for the magnetic component. So referring to the inductor. And then you also can find the minimum inductor by using this equation. Similarly, you need to actually to design the flank capacitor. So how you can design? You can use these equations, and then from this you also can get actually the minimum capacitance of the capacitor. So how minimum the capacitance of the capacitor. Therefore, from there you also can reduce the value, and also you can use ceramic capacitor or film capacitor because it's very small, but very tiny as compared to the electrolytic. So therefore, this is also very important for you to find as minimum as possible. Then you can use either ceramic or film capacitor as compared to electrolytic. So this is the experimental result. So shows that this is the characteristic of the VDS device and also the inductor current for this one. So therefore, at the same time, the the flank capacitor for the third level can be estimated based on the voltage source and the capacity because the same. The voltage is same. So therefore, means that if you reduce the voltage stress on the VDS by estimating the C, means that you also can reduce the rating of the MOSFET or for the semiconductor. Then you can select the appropriate type of MOSFET or semiconductor that will be used for that system, for the system. So this is the capacitance versus voltage stress on the switching devices. So from the 7 level, 5 level, and 3 level. And also the influence of the time constants, RC. Is it influenced or not by the switching frequency? So from this analysis, it's not influenced. If you change RC, the output side, this side. This RC factor will not affect the switching frequency. Means that you can increase switching frequency regardless of the factor tau factor or the constant factor of R and C at the output side. Okay. Then you can use this equation to represent for the switching voltage side at the switching side. So this is only the operation mode. If you want to learn this one, it's something like the operation mode 1, charging, mode 2, the power is the L is discharging to the output. Then mode 3, current capacitor discharging to the output sides. Then mode 4, this is the simple mode. And this is for the 5 level. And then this is the experimental result to prove that is it stable or not, the output. For example, this is the output voltage, current capacitor voltage. Then this is inductor current. Then this is the current capacitor at the I think this is for 5 level, VFC1, C2, and C3. The output ripple is very small actually. So from there you can use very small capacitor. In this case, either film capacitor or the ceramic capacitor. So the VFC is consistent, all consistent. So it's not influenced by the changing of this D. Okay, this is the ripple voltage of flank capacitor versus capacitance of the flank. Actually, for this study, I try to challenge other people. So researchers during that time, they said that for the flank capacitor structure, we need to use high capacitor. But I challenged that guy. Actually, we can use very small. And I prove it that this is possible. So by proving the many angles, so many parameters, actually we can use very small capacitor for the flank capacitor in order to as a energy transfer agent to the process. Okay? Sorry, this is very what analysis level. So I think sometimes difficult to understand, to absorb, or to appreciate this one. But and then, as Paolo said, is in order for you to design any converter, you need to consider this parameter. Efficiency is very important. For example, in this case, I try to get more than 1 kilowatt power, and the power is minimum 96% and above. So means that even though you use very small, if you see 1.1 microfarad, it's very small. 0.6, very small. 0.5, very small. This is 0.11 microfarad, it's very small. This is film capacitor. So means even though we use very small capacitor, with properly designed, we can achieve very high efficiency of the converter, even though more than 1 kilowatt converter, isn't it? Okay. So in this case, I prove that by using very small flank capacitor as a transfer agent to the output side, we also can achieve very high efficiency. And then finally, by using Pareto curve, we can achieve the optimum points as compared to 2 level. So we can maintain more than 98% of the efficiency for both cases. At the same time, we can get higher power density of the 3 level as compared to the 2 level. So means that I can challenge that guy. At the same time, I also can contribute to the body of knowledge. So actually, we can get both high power density at the same time, high efficiency at the same time. So this is my work before. Okay, before that, any question?
What is the disadvantage of the N-level FCBC?
Many component.
And what about the complexity of the control?
Okay, control also will be complicated, yeah, because in this case, okay, the switch will be increasing. The switch here will be increasing. If you increase the level, the switch will be increasing, isn't it? So once the switch increasing, the control also will be complicated. So in this case, I only use for the PI control for the VNI. Okay. Any other question?
Just reminder, it's now 10 o'clock.
Oh, 10 o'clock. Okay, okay.
Okay, perhaps you can go through until 10 minutes more.
Okay, okay, okay. Now I think I will stop here. Actually, there are second part, but I think we have no time. Okay. Okay. Before we wrap up, is there any other anything you want to ask or any questions from the floor? From the member floor?
Okay, for all the participants here, please, if you have any question, just ask now directly to Professor Asmar Rashid. Any questions? Or perhaps this topic is too complex for the participants here.
I think I think the first part is very easy. The first part.
Yeah, the first,
I
the first
divide
part
two
is
part. Very easy.
really,
The second part is quite
basic.
heavy.
It's
But I think
fundamental.
I cover all from the fundamental until the high. I think should be fair to all, isn't it? Because Pak Baru also here. So I think
Yes, very fast the participant breakdown.
So regarding my question about the complexity of the control, so until which level? 5, 6, or 7 level, the complexity of the
Seven,
control
seven.
can be coped well.
I think only up to 7 level.
Up to 7 level.
7. After that will be more, I think it's difficult. Difficult to control and difficult to make it the control part.
I see. So for the controller implemented in what kind of controller? Microcontroller or special circuit like FPGA or what?
I'm using FPGA and FPGA to generate for the switching scheme and what the DS control, what?
DSP.
This is the control using the PI control. Then with the FPGA.
I see. It's a really complex circuit. If we use the but how we can measure the complexity in this case?
Okay, in this case,
we can compute Pareto from the efficiency, the power density, but what about the complexity? How can we accommodate this complexity number into the Pareto frontal from here?
Okay, in this case, for this one, I don't include the complexity of the control part. I focus on the structure only in this case.
I see.
So in this case, if the complexity is the concerns, I think 3 is enough. I mean, 3 level is enough because only two MOSFET enough is compared to the 7 level.
Okay, but we can measure it quantitatively for sure.
Quantitative? What you mean?
I mean, how can we express the complexity using number?
Oh, number. Okay. if I compare with the conventional boost converter, for example, three level is as compared to CBS, I think the complexity of the control only maybe 20% to complex as compared to the conventional boost converter because it's only additional one MOSFET.
Okay.
Uh,
So we measure this. How can we compute the complexity number?
yeah, I'm not sure how to go, but if I refer to the switches, I mean number of switches, I think we can refer that. Means that, for example, for the conventional converter, only one switch. So I think very easy to control. Then for the three level, two switches, and so on. So means that if we refer the main number of switches, so we can estimate how complex the control required. So I think in this case, three level is good because only two switches. In fact, actually GDU, you can use one GDU for two switches. Because if we can make sure that the GDU can hold the power up to 500 milliwatt, actually we can one GDU for two switches.
Okay. Here one participant want to ask you. Okay. This is from Avicen Hawkins. He
Please,
asked. Yeah, he asked. The question is, do they use MOSFET on high converter or use relay instead? Some relay had limit about 100 kilo click or transition. So which one will be used on high? Must be high power converter or high voltage converter. MOSFET or relay instead.
Okay. For example, if you use line frequency 50 Hz, I think relay is easier.
Okay.
But if, for example, 10 kilohertz, 1 kilohertz, 100 kilohertz, you should use MOSFET. Impossible relay can cope. Impossible.
Yeah.
And either low power or high power, I think we don't count that. But as long as the frequency is possible, for example, 50 Hz relay, more than that, I think must be semiconductor devices.
Okay. But the consequences, the inductor and the capacitor must be very, very,
Exactly.
very large.
Yeah. Very bulky, very hard.
That will be impractical.
Yeah. Usually we don't only consider for the ideal case, and we also need to consider the practicality. Is it practical or not? So that's very important. In order for us to make sure that our projects or system can be depart to the industry, we need to consider practicality aspect.
Okay, it's now 10 over 8. I think it's enough for now for the lecture from Professor Asmar Rashid. For all the participants here, if you have any question, perhaps you can contact directly to Professor Asmar Rashid for
Sure.
discuss. Okay, and I will give the screen back to Profesor Rini. Okay, here Profesor Rini.
Terima kasih Pak Waru. Terima kasih juga untuk semua peserta. Ya. Sayang sekali waktunya sudah habis. Terima kasih Prof. Asmar Rashid. Nanti kalau kami mengundang Prof. Asmar lagi, kami akan undang yang lainnya juga.
Sure.
Ya, masih bisa ikut mendengarkan ataupun belajar dari Prof. Asmar. Terima kasih sekali lagi.
Terima kasih banyak semua.
Terima kasih dan mungkin sampai jumpa lagi Prof.
Ya, insyaallah Prof.
Segera datang ke UP juga. Nanti sebentar ada link presensi ya untuk yang menginginkan sertifikat. Sebentar mana tadi ya. Ini ya.
Saya dapat sertifikat nggak, Bu Rin?
Ya, udah kalau itu. Untuk yang menginginkan sertifikat, silakan isi presensi. Dan sangat berterima kasih atas ini waktu dan ilmunya Prof. Asma.
Baik, terima kasih.
Sehat selalu.
InsyaAllah, terima kasih Ibu Rini, Prof. Rini dan juga Pak Baru. Terima kasih banyak
Terima
atas
kasih.
jemputan.
Sampai jumpa. Sampai jumpa juga untuk semua peserta.
InsyaAllah, terima kasih banyak.
Oh, ini
Assalamualaikum.
Sampai jumpa
katanya
semuanya. Assalamualaikum warahmatullahi
minta
wabarakatuh.
materinya katanya.
Boleh insyaAllah.